Project 5. What are electron bands? The electrons in an atom tend to organize themselves into specific regions with higher or lower energy levels. The electrons prefer to exist in the lower energy levels, and as such will fill the lower levels first. The highest two energy levels are called the valence band, which is the highest energy and completely filled level, and the conduction band, which is one above the valence band and is either partially filled or completely empty. Electron band gaps are the difference in energy levels between two bands. The space between them is the amount of energy it requires to bring an electron up to the next band, or the amount of energy released when it drops down to the previous band. An insulator is a material which does not allow the passage of energy or electricity. For example, glass is a good insulator. Insulators behave this way because the gap between the valence and conduction bands is high, and the conduction band is empty of electrons, meaning it takes a large amount of energy to bring an electron from the valence band to the conduction band to start conducting electricity. A conductor is a material that conducts or transmits electricity well. For instance, graphite and copper are both good conductors. Conductors transmit energy well because the conduction band has free electrons that can move around with low resistance, but is also not entirely filled so as to impede energy movement. A semiconductor is a material with conductivity and properties in between that of an insulator and of a conductor. Devices made of semiconductors are often essential components of electronic circuits. A semiconductor has special properties because the gap between the valence and conduction bands is small, so an electron can jump between the bands and start conducting electricity without very much energy required.
There are three different types of bonds. The ionic bond forms between metal and nonmetal, where the metal donates a valence electron to the nonmetal. These types of bonds are strong. The covalent bonds form between two nonmetals, where the atoms share valence electrons to satisfy the octet rule, and these types of bonds are most common in living organisms. The metallic bonds form between metal atoms, where valence electrons float between multiple atoms. These bonds are weaker than the ionic, but stronger than the covalent. We have the van der Waals forces. The weakest of the intermolecular forces, van der Waals forces, require a dipole molecule to be near another dipole molecule. Then the opposite charged poles attract. Hydrogen is just one example, requires one or more hydrogen atoms bonded to a highly electronegative atom, such as H2O or HF. When two of these molecules are with the vicinity of each other, the opposite charged poles will also attract. Resistance can be seen as a material's property that opposes the flow of an electric current. You can see the series formula is resistance 1 plus R2 plus R3, etc. And series is longer in length, which means the electrons have to travel through more materials, thus increasing its resistance. We then have parallel, which is 1 over R1, 1 over R2, etc. And parallel has a larger cross-sectional area, which means that it allows more electrons to pass through it. We have our resistance formula up here as well. Resistance equals the resistivity times the length of the wire over the area of the cross-section. We then have conduction holes. If an electron band gap is nearly full, with only a few empty spots, these are called holes. A hole can be treated like a singular positive charge and behaves like an electron with opposite charge, and can also move around a conductor or semiconductor similar to an electron. We then have types of semiconductors. A semiconductor, again, can be seen as a solid with electrical conductivity between that of a conductor and an insulator. So we have the first type is mobility. It's how much effort electrons and holes can move through a semiconductor material when an electric charge is applied. We then have the intrinsic, which is a pure semiconductor, such as silicon. Intrinsic semiconductors have a low conductivity. And then we have the doped semiconductor, or the extrinsic, and they are impure semiconductors. A small amount of controlled elements such as boron or phosphorus. This addition of another element increases or decreases the amount of valence electrons, which makes the conductivity greater.
The band gap in gallium arsenide is larger than gallium phosphide, so the electrons release more energy when falling back down to a level. This higher energy outputs a result in a higher wavelength and a different colored light. For this example, gallium phosphide produces a wavelength of 555 nanometers, which is on the visible light spectrum, which is a green light, while gallium arsenide produces an 850 nanometer wavelength, which is in the infrared scale. We were tasked to find the properties of silicon as a semiconductor. We need to find the mobility of electrons in holes at 300 Kelvin, the concentration of free electrons and free holes of intrinsic silicon at 300 Kelvin, the electrical conductivity at 300 Kelvin, also the resistance along the length of a silicon resistor that is 1 millimeter squared wide and 1 centimeter long. And then what is the resistance if the temperature was increased to 700 Kelvin? Silicon's electron mobility is 0.85 meters squared per volt second, and hole mobility is 0.45 meters squared per volt second. Silicon's intrinsic concentration is 1.3 times 10 to the 16th per meter cubed. The energy of a single electron of silicon is 1.6 times 10 to the negative 19th joules. And to find the electrical conductivity of silicon, it is this equation right here. Then to find it, you just sub in all the previous values, and then you get 2.704 times 10 to the negative third ohm meters. And then the resistivity is just 1 over the conductivity, which is 369.822 ohm meters. To find the resistance of silicon at 300 Kelvin, you need the resistance formula, which is resistivity times length over cross-sectional area. Using previous values and plugging in for resistivity, length, and cross-sectional area, you get 3,698.22 ohms. For resistance at 700 Kelvin, first we need to find the intrinsic concentration of silicon at 700 Kelvin, which is 2.145 times 10 to the 28th per meter cubed. Next, we need the conductivity of silicon at 700 Kelvin, which is 4.461 times 10 to the 9th, and the resistivity at 700 Kelvin, which is 2.241 times 10 to the negative 10th. Now finally, we can calculate the resistance of silicon at 700 Kelvin, which you plug in all of those values into the resistance equation, and then you get 2.241 times 10 to the negative 9th ohms. Next, we are doping silicon with 2 times 10 to the 19th per centimeter cubed boron atoms. We have to find the values for N and P at 300 Kelvin, the electrical conductivity, and the resistance along the length of a silicon resistor that is 1 millimeter squared wide and 1 centimeter long. Also, the resistance if the temperature was increased to 700 Kelvin. We know that boron is an acceptor. That's pretty cool. The intrinsic value of silicon at 300 is 1.3 times 10 to the 16th meters cubed. The value for P is 2 times 10 to the 19th, and the value for N is 6.5 times 10 to the 12th. And using the equation for conductivity, you get 1.44 ohm meters. And then using the equation to find resistivity, you get 0.694 ohm meters. And then finding the resistance of this doped silicon, you use the resistance equation, and then the resistance you get is 6.944 ohms. If the temperature was increased to 700 Kelvin, the resistance would stay the same, since the value of P, the positive amount of charge, is unchanged.